Okay, and then we get to this this idea of enthalpy. So let me introduce this idea to you. Enthalpy is one of the biggest ideas inside of chapter 6. It's basically what we deal with for the rest of chapter 6. And then it is probably one part out of 3 parts that all come together to make up chapter 17. So welcome to enthalpy. Enthalpy is represented by an H. The variable for enthalpy is an H. It is a specific form of heat energy. So it's enthalpy is a form of energy, but it's a form of energy that looks at heat alone without looking at work. Here's the definition for enthalpy. It is heat transferred under constant pressure conditions of the Earth's atmosphere. So it's heat transferred when pressure remains constant. So you can think of circumstances where this might be true, right? If you have a beaker and inside your beaker you are producing gas and the gas is flowing out into the atmosphere, well, remember that gas, in order to change the pressure of the atmosphere, that gas has to change the pressure of like the entire Earth, right? Or if you're looking under a technical definition in thermodynamics, it has to change the pressure of the entire universe. Well, gas that we produce in this room is not going to change the weather patterns around us, right? It's not going to change atmospheric pressure. It's not going to change the pressure of the universe. And so anything with an open top would be considered constant pressure. So how could we create a system that would not be constant pressure? What would a variable pressure system look like in our lab? Pause this here and think about this a little bit. See if you can come up with a system. And the answer is not difficult. It's just to put a lid on it, right? If we take a system and we put a lid on it, it's no longer constant pressure because now whatever gas we produce inside this closed system is going to change the pressure of our system. So think about so you have a jar half filled with water, you put a lid on it and you put it in the microwave. What's going to happen? It's going to explode, right? Because all of a sudden you're building up pressure inside this glass jar. Glass doesn't contain pressure super well. And so the glass that pressure eventually is going to crack the glass, right? That would be a variable pressure situation. You change the pressure inside your container until you crack the glass, right? So anything without a top is going to be constant pressure. Anything with a top will be variable pressure. So if you're talking about enthalpy, you're talking about the heat transferred inside a constant pressure, also known as open system, right? If your system is closed and the pressure inside can go up and down, you can't talk about enthalpy anymore. So it's just kind of like a condition. If you are going to set up a lab to measure enthalpy, you just have to make sure that it's a constant pressure lab and not a variable pressure lab. So open containers and beakers, only tiny amounts of work are done. Again, remember, in order to have work done, you need a change in volume. If your beaker is open, that means your volume is the beaker and the room and the earth and the universe. You're not going to change pressure, you're not going to change the volume of that. And if volume change is 0, therefore work change is also 0. Same thing with pressure. If you have, same thing would not be with pressure. Okay, so in a constant pressure situation, your volume change is going to be 0, therefore your work is 0. If your work is 0, work is 0, that means that energy is due to heat only, and that heat right there is what we call enthalpy. So enthalpy is heat transferred under specific conditions, and the specific conditions have to be constant pressure. Now, when you're dealing with enthalpy, as you're reading through the text, as you're working through problems in the back of the book, what you really need to be careful of is what is written as a subscript down here. Before we dive into this, I just want to make you aware that the little subscript they put after the H tells you what the context is. Is it the enthalpy of the reaction? Is it the enthalpy of the solution? Is it enthalpy of neutralization? Is it enthalpy of formation? That little subscript tells you what the context is, and the context determines your reaction. So be aware of that subscript. It makes a really big difference. Last note, you might see them call it enthalpy. You might see them call it heat. They use the two interchangeably. Enthalpy of reaction is the same thing as heat of reaction. The change is measurable. It's always a relative number, final relative to initial. Okay, so we can measure the change. We're always going to be measuring the change. We're never going to be measuring enthalpy of a system where it stands right now. We're always measuring the change relative to final and initial. Okay, so we'll stop there for today. I think that's enough information. We'll go back and try some of those practice problems tomorrow. And in the next video, we'll pick it up right here with enthalpy. Have a great day. Good job, you guys. So let's keep going here with enthalpy. Enthalpy, like we said before, is going to be a measurement of heat transferred, right? And so in order to talk about change in enthalpy, you're going to compare the final enthalpy and the initial enthalpy of your system, and that will give you the change in enthalpy. And that's what we see here. So we have change in enthalpy is equal to final minus initial, which in chemistry is usually we don't say like final molecules and initial molecules. We say products and reactants. So it's enthalpy of the products minus enthalpy of the reactants. That will give you the change in enthalpy. You might see enthalpy as a delta H, like we talked about on the other slide. You also might see it as a Q with a subscript of P. Remember, this comes from the formula energy equals work plus heat. So Q is heat. And when they give that subscript of P, that P means heat under a specific condition of pressure. And so in order to talk about enthalpy, it needs to be heat when pressure is constant. So you might see it as delta H, you might see it as QP. They mean the exact same thing, either way. And then again, like we talked about on the last video, the sign is going to indicate the direction that heat is transferring. So again, always come back to this idea of from the perspective of the system. So if enthalpy is positive, that means the system is gaining enthalpy. The heat is being transferred from surroundings to the system. If you are holding the system in your hand, you are the surroundings. So that would mean that heat is transferring out of your hand into the system. If heat is leaving your hand, that's going to feel cold. That's endothermic. Into the system. It's hard to make that shift of thinking from the perspective of the system instead of thinking from your perspective, right? In this case, most of the time, we are the surroundings. So we can't think from our own perspective. We have to think from the perspective of the system. If it's negative, the opposite is going to be true. So if delta H is a negative value, then from the perspective of the system, energy is leaving the system. That's exothermic, out of the system into the surroundings. Again, if you're holding that, you are the surroundings. Out of the system into the surroundings means energy is entering your hand, and that's going to feel warm. Okay, so just another pitch here to understand those signs, not from the value of a number line, but to indicate a direction of heat flow. All right, fun facts about enthalpy. We have about 4 different fun facts. So first of all, enthalpy, unlike heat, enthalpy is a state function. Remember, heat's not a state function. Heat is pathway dependent. We talked about how on that energy diagram, energy was a state function. Energy just depends on where it starts and where it finishes. Work and heat are not. However, when you're talking about Q under constant pressure, remember, work is going to be 0. So that means that all of the energy of the system is changed in heat. And in this case, since energy is pathway independent, that means that QP is also pathway independent. So enthalpy is a state function. Heat is not. Heat under constant pressure is. It's also an extensive property. We talked about this word way at the beginning of the year, maybe actually on the first day. Extensive and intensive. So it's an extensive property because it is dependent on the amount that's present, right? We talked about how something like color is an intensive property. Color doesn't matter if you have 1 cotton ball or 75 cotton balls, the color is going to be the same, right? But something like mass is going to be an extensive property. Mass depends on how much is there. If you have a teaspoon of water and a swimming pool of water, then your mass is going to change. It is extensive. Well, enthalpy is also extensive. It's going to change depending on what is there. So if you, let's say, 483.6 kilojoules of heat is released for every 2 moles of H2 burned. Well, then if you burn 4 moles, you're going to get double the amount of heat. If you burn 12 moles, you're going to get 6 times the amount of that heat. So enthalpy is an extensive property. It matters how much is present. And so the enthalpy for this reaction that we see here is going to be different than the enthalpy for this reaction. Oh, that's it. Okay, so what would the enthalpy for that reaction be? Can you beat me there? Okay, all I did was double the coefficients, right? But that doubles the amount that I'm dealing with, and therefore it's going to double the total amount of enthalpy. So you have to be careful with this, whether they deliver enthalpy to you per reaction or they deliver enthalpy to you in a ratio, because that's going to matter how you deal with it. Okay, number 3, If you reverse the reaction, you are going to have an enthalpy that is equal in magnitude but opposite in sign. So for example, this reaction in number 2 here, let me erase what I have. Okay, the amount of energy for this reaction here, it's negative, right? 483 kilojoules negative, which means that heat is released out of the system into the surroundings. Well, if you flip the reaction, notice here they have reversed the reaction without changing any of the coefficients. They just reversed it. So when water falls apart into hydrogen and oxygen, the enthalpy is equal in magnitude but opposite in sign, which indicates that in this case, the heat is not released from the system into the surroundings. Heat is actually absorbed from the surroundings into the system. So if you reverse the reaction, the enthalpy is going to be equal in magnitude, opposite in sign. Number 4, enthalpy is going to be dependent on the state. If you have a reaction like the reaction in number 2, and notice that we have created water vapor, if you have that same reaction and instead you make water as a liquid, that is going to be a different enthalpy change. So enthalpy is specific to the state. Notice that just changing the state here has a specific enthalpy. So what is the state change that occurs here? Liquid to gas is going to be vaporization, right? So this enthalpy, 88 joules, it's the enthalpy of the vaporization of water. So we could label it as such. Enthalpy of vaporization of water is 88 joules. In order to take water from a liquid and turn it into a gas, in order to take 2 moles of water from a liquid and turn it into 2 moles of gas, the water, our system, the liquid water, needs to absorb 88 joules of energy from the surroundings in order for this phase change to occur. So enthalpy is dependent on the state. You have to be careful which states you are talking about. All right, now would be a good time to pause this video and see, can you name these 4 things off the top of your head for enthalpy? Okay, let's talk about this example. When 1 mole of methane is burned at constant pressure, 860 kilojoules of energy is released as heat. Calculate delta H for a process in which 5.8 grams sample of methane is burned at constant pressure. So pause this, see if you can beat me there. Now, a couple things about here. They tell you that it's constant pressure so that you know that the delta H that you're dealing with is enthalpy. If, for example, methane was burned inside a closed container, then the pressure would build up inside here, and it would not be a constant pressure scenario, and you would have to deal with the work that was done as well as the heat that is released. So by taking this and burning methane under constant pressure, right? When we burn methane, we're going to release gases, but those gases aren't going to change the pressure of the universe. So we can assume that the pressure released, the gas molecules released, have a negligible effect on the atmospheric pressure or the pressure of the universe. And we can call this enthalpy. Okay, so it's 1 mole of methane, it's burned at constant pressure. 860 kilojoules of energy is released as heat. Now, I'm going to write out the reaction here just so you have a very clear picture about what is going on. You don't actually have to write out the reaction for this problem. but you have methane being burned, you should be able to write out the reaction for this. And then, of course, we have to balance it. There we go. And so the enthalpy for this reaction is 860 kilojoules. And notice it's specifically for 1 mole of methane. And when I balance this reaction, I need to balance it so that I get 1 mole of methane. Now, it just automatically balances out nicely for us. But if I had balanced it and gotten like 2 moles of methane, I would have just had to divide all the coefficients by 2 so that I'm balancing it specifically for the amount of methane that they tell you the kilojoules is linked to. Okay, so 5.8 grams of sample of methane is burned. What is delta H in this case? So 5.8 grams of methane. Now, we're not in grams, we are in moles. So we want to bring this from grams to moles of methane. And then we want to get it out of moles and into enthalpy. Okay, so molar mass, let's see. For 16.042 per 1 mole. And then this ratio, can anyone come up with where that ratio comes from? This ratio is communicated to you in your paragraph somewhere. It's 1 mole for every 1 mole of methane burned. 860 kilojoules of energy is released. That fraction is this sentence right here. So they give you your conversion factor in your sentence. And now we just plug and chug. All right. Oh, really? No, that's not right. Okay, 310.93 kilojoules is what I got. Okay, now you need to think about signs. So here's an extra step when you're looking at like a problem in this chapter. You need to deal with the math. You need to get your magnitude, and then you need to pause and evaluate the signs. Signs are the most important part of this chapter. This is the skill you're going to learn to deal with in this chapter. Okay, so let's pause and think about signs for a second. Okay, when 1 mole of methane is burned, 860 kilojoules of energy is released. So what should the sign be on this? Should that sign be positive or negative if energy is released? From the point of the system, the energy is going from the system into the surroundings, released into the surroundings. And so that should be a negative. Now, if you put a negative here, your answer would come out negative also. Or you can sit and think at the end, okay, I'm burning 5.8 grams of sample. Heat is going to be released from the system to the surroundings, so my answer should be negative. Ta-da! And there you go. Now we can evaluate significant figures. We have 2 here and 2 here, so we really should be keeping this to negative 310 kilojoules. That should be your answer. All right. Okay, so a couple different conceptual pieces to think about as we're processing this through, but it all comes back to kind of the same dimensional analysis, right? It's the beauty of most of these questions in chemistry. Most of them come down to dimensional analysis. All right, we'll try this one in class together. Okay, let's expand our understanding here of energy. All right, so This is the equation we've been talking about all along. Total energy equals heat plus work. We're going to plug in these two parts. So for heat, we're going to assume it's constant pressure. And for work, we're going to plug in this equation also. And so when we do that, we get this equation right here. So again, the condition for this equation to be true, it's only going to be true under constant pressure, right? In order to be dealing with enthalpy instead of heat, we have to be under constant pressure. But as long as that is true, we can deal with this formula. And so it's another formula that this chapter introduces to you. Might be helpful to kind of keep a formula page as we go through here, or to pull out your reference sheet and make notes about which of these formulas are on your reference sheet and which of these formulas are not. Okay, come on. Okay, so on this problem, there's a couple problems that your book kind of goes through in order to deal with this equation. We don't deal with this equation a whole lot, so we'll just keep it in our back pocket in case we need it later. Okay, so here's where we get to now. We get to possibly the biggest idea of chapter 6. This is calorimetry. So calorimetry is a lab technique that allows us to measure the heat transferred or the energy transfer of reactions. So there's a couple different things we have to talk about before we really apply this idea of calorimetry. Okay, so stay with me on this. So calorimetry is a lab technique that measures heat flow, measures the transfer of energy, but specifically in terms of heat flow. And a calorimeter is a device that allows you to do that. So a calorimeter basically is any device that traps the heat inside of your experiment and doesn't allow the heat to transfer into like the device or the atmosphere beyond the device or just kind of into the air. So it traps the heat, it doesn't allow it to escape. These can be pretty simple devices. They can be extremely complicated devices. We tend to use styrofoam cups as our calorimeter because styrofoam is very successful at trapping heat, especially for our intents and purposes. Our thermometers are not like ridiculously sensitive thermometers. And so a calorimeter will trap enough heat so that we really aren't able to detect the amount of heat loss with the thermometers that we actually have. So styrofoam cups work very well. Okay, the other thing you have to know is this idea of heat capacity. Okay, so heat capacity is represented by a capital C, and it reflects the temperature change when energy is absorbed. So basically, like as your thing absorbs energy, how much does the temperature of your thing change? And you can think about stuff sitting on your stove. Let's say you have a pan, an empty pan sitting on your stove. Okay, you may have actually done this. So an empty pan sitting in your stove, what is your pan made out of? Your pan is probably made out of some type of metal blend, maybe aluminum. Let's say your pan is made out of aluminum. As you turn that stove on, there's going to be heat or energy that's given off from the stove into the pan, right? So the question would be as that energy release occurs, how fast does your pan change temperature? Now think about if we were comparing an aluminum pan to, say, a cast iron pan. So if any of you have done cooking before, you will know that a cast iron pan, they're usually black. Some of them are fancy, and so that you get fancier colors. Okay. They're usually really, really heavy. If you have the same amount of iron sitting on your stove versus aluminum is not a very dense metal. It tends to be much lighter. Okay. So we're going to put 2 pans on the stove. As that energy release occurs, the temperature of your aluminum pan is going to spike really fast. The temperature of your iron pan is going to take forever to actually get up to a hot enough temperature where it's going to sear your food. It's going to grill your zucchini. It's going to sear your pork. It's going to do whatever you need it to do, right? Because the heat capacity for aluminum is a lot different than the heat capacity for iron. Okay, for the same amount of energy, let's say the heat capacity for aluminum, let's say it has absorbed 1 joule of energy, but it has changed 100 degrees Celsius. If we compare that to the heat capacity for iron, when iron has absorbed that same 1 joule of energy, it will have increased maybe 20 degrees Celsius. Iron changes temperature much more slowly because it has a different heat capacity. So this is kind of the idea of heat capacity, and this extends to all kinds of things. I mean, if we filled these pans with water, then that would change the amount of temperature, right? If you're going to leave an aluminum pan on your stove, you're going to burn through your aluminum pan quite quickly. But if you leave an aluminum pan with water on your stove, it's not going to burn through. That same amount of energy is not going to change the system's temperature as quickly, right? So different things, different metals, different substances are going to have a different heat capacity. So you have to know the substance that you're dealing with in order to measure heat flow in or out of that substance. Now I'm going to post something online for you guys to play with a little bit that will allow you to kind of play with this idea of heat capacity and kind of wrap your brain around it. Notice that the equation for it is heat absorbed over increase in temperature. And so for heat capacity, you're going to come out with specific units. Can you tell me what those units are going to be? So it's going to be joules per degree Celsius or joules per degree Kelvin, depending on what you're measuring your temperature in. And then out of this idea of heat capacity comes 2 other concepts. So we have this concept of molar heat capacity, and we have a concept of specific heat capacity. So both of these are heat capacities, but they are, they're just kind of zeroing in the conditions under which heat capacity is measured. And so molar heat capacity is going to be the same idea. What's the increase in temperature per heat absorbed, or I guess it's vice versa. What's the heat absorbed per degree temperature change per mole for specifically 1 mole of the substance? And so the units that come out of here are going to be joules per Kelvin mole. So you can kind of put this into a sentence. How much energy does it take to raise the temperature of 1 mole of substance 1 degree? That would be molar heat capacity. How much energy does it take to raise the temperature of 1 mole of substance 1 degree? right? Okay, now specific heat capacity is very similar, but instead of being 1 mole of substance, it's going to be 1 gram of substance. So your units are just going to come out slightly different, joules per Kelvin, again, but per gram. Now, this is especially useful for dealing with some things like macroscopically in our lab, like an almond. If we want to know how much energy is released per gram of almond, it's a lot more convenient for us to measure the mass of an almond in grams instead of measuring the mass of an almond in moles, right? If we're dealing with something like iron or aluminum or water, it's not such a big deal. Like we can figure out what the molar mass of water, aluminum, and iron are and deal with the moles of that. But when you're dealing with something like an apple or almonds or some other type of mixture, it's a lot harder to figure out what the moles are that are present. And so it's much more convenient for us to deal with the whole mixture together and just measure it in grams. So molar heat capacity deals with this concept per 1 mole. Specific heat capacity deals with this concept per 1 gram. Okay, so let's take a look at what the next slide is. I don't want that. So just last thought here, and then we'll kind of revisit practice problems on the next video. But there you can start with their idea of a specific heat capacity in joules per Kelvin gram, and instead, and you can actually turn this into a formula. So here we have a formula for specific heat, which is the quantity of heat transferred per gram per temperature change, right? And basically what we're doing is we're taking this idea and we're looking at each of these different components in a measurable way and then putting them together to calculate out what the specific heat capacity would be. So if you can figure out what the energy change or the heat change of the solution is, divide that by the mass of your substance that you're dealing with and the temperature change that has occurred, you are going to calculate out the specific heat capacity of your substance. So, like all of our equations, I'm going to encourage you to derive this, not memorize this, right? Anytime you have these units, you should be able to piece your way through a formula, right? Joules is going to come from heat. K is going to come from temperature. And then G is going to come from your mass. And those things, Q divided by M delta T, is going to give you your specific heat capacity. So I highly encourage you to derive this equation, not memorize it. Again, check your reference sheet, see if it's there. But this is the equation we're going to kind of move forward with into our calorimetry labs. Now, I do want to stop here so that you can visit that kind of heat capacity simulation and play around with it a little bit and wrap your brain around heat capacity before we try to apply it into labs. So great job. See you in class. Enjoy.